Welcome to this lecture covering two knowledge representation strategies, specifically trees and rules. During this lecture, we'll start by introducing knowledge representations and knowledge bases. Then we'll take a brief look at knowledge representations in the context of machine learning. Then we'll take a closer look at trees as one form of knowledge representation, and lastly, rules as another. Let's start off with knowledge representations and knowledge bases. Recall that the topic of knowledge representation is a subfield of artificial intelligence dedicated to transforming information from the real world into a specialized and/or structured digital format that a machine can use to perform complex tasks such as reasoning, learning, problem-solving, and mutual understanding. We previously introduced a number of knowledge representation strategies that are commonly used in artificial intelligence, categorized here as traditional and logical strategies, structured and contextual strategies, and probabilistic or other modern strategies. One of the traditional and logical knowledge representation strategies were production rules, or more generally we'll refer to them here simply as rules. Closely related to rules, we'll also add trees, or more specifically decision trees, to this list for this lecture's discussion. Now let's take a moment to define a knowledge base. This is a specialized repository that stores complex, structured, and unstructured information used by a computer system to solve problems or make decisions. Unlike a simple database, a knowledge base is designed for knowledge representation. In other words, not just capturing data, but also the relationships, rules, and logic that define a specific domain. Some key components of a knowledge base include a fact base, inference engine, and a knowledge representation scheme. A fact base is a collection of specific declarative facts about a given domain. For example, drug X targets protein Y. An inference engine is the brain of the system that applies logical rules to the facts to deduce new information or conclusions. And we've already defined knowledge representation schemes, including examples like logical representations, rules, and ontologies. In this table, we summarize some high-level differences between a traditional database and a knowledge base. With respect to content, a traditional database includes explicit data entries, while a knowledge base includes explicit facts as well as implicit rules. With respect to processing, a traditional database focuses on retrieval or querying, while a knowledge base focuses on reasoning through inference. And with respect to intelligence, a traditional database is static, returning only what is stored, while a knowledge base is dynamic and can derive new facts. Experience suggests that intelligence systems require large amounts of domain-specific, real-world knowledge to achieve anything useful. Consider that humans often tackle difficult real-world problems using their knowledge resources, for example, experience or training. A representation in a knowledge base should ideally be interpretable for humans, allowing the encoding of information and knowledge base without significant effort, and allow understanding of what the system knows and how it draws conclusions. Ultimately, knowledge representation schemes and reasoning methods must be coordinated and compatible within a knowledge base. This slide briefly reviews the knowledge representation strategies that will be covered in this course. We start off here covering trees and rules, and in other lectures we'll cover logical representations, including propositional logic and first-order logic, semantic networks and other related representations, frames, scripts, and knowledge organization systems, including folksonomies, controlled vocabularies, taxonomies, ontologies, and semantic webs. Now we'll briefly discuss model representations in the context of machine learning in particular. One of the biggest differences between machine learning algorithms is how knowledge is represented in the model. For example, a linear regression model is represented as a standard mathematical function, including a dependent variable, independent variables, and coefficients. Then we have neural networks, with a model represented by nodes and edges making up a network. On the left, input nodes take in feature values. These are transformed and passed to other nodes along edges, ultimately leading to one or more output nodes where a prediction is made. Then we have support vector machines, where the model is a hyperplane that seeks to best separate instances by class. Also, there's decision trees, which organize a hierarchy of conditions leading to a decision or conclusion. And lastly, we have rule-based machine learning, where the model is represented by a set of independent or hierarchical if-then rules, working together to make predictions as an ensemble. When you hear the term machine learning, you should be aware that it's a general term for a wide variety of algorithms. These cartoons illustrate different families of machine learning algorithms. It's important to be aware of the variety of algorithms available, each having its own unique strengths and weaknesses. These algorithms can differ by how they represent knowledge, how they search a problem space, how they learn, and by the assumptions they make, either implicitly or explicitly. Let's take a moment to illustrate how the use of different machine learning algorithms and the underlying representations they employ impacts how different problems can be tackled. First, let's say that we have 3 datasets with just 2 important features in each, represented by the values on the x and y axes. For each, the task is binary classification, or distinguishing data points labeled blue from red. The bottom dataset has what looks to be a mostly linear separation, with blue points on the left and red points on the right. The middle dataset has mostly blue instances in the middle and red instances on the outside. And lastly, the top dataset has what appears to be a yin-yang pattern separating the 2 classes. Let's take a look at how this set of 7 machine learning modeling algorithms model decision boundaries in each dataset to predict either class blue or class red. Applied to the first dataset, these algorithm models yield the following decision boundaries, illustrated here by the background colors behind the data points. In each, the darker the blue or red, the higher the probability, based on the model, that an instance found in that part of the problem space would be one class or the other. Any instances that fall within a blue area would be predicted as class blue, and vice versa. In the bottom right of each plot, we can see the respective testing accuracy achieved by each algorithm. On this first dataset, which includes modeling a fairly simple linear separation between classes, all algorithms perform similarly well. However, you can see the variety of how these different algorithms make decisions based on differences in both the shape and class probability gradient of their respective decision boundaries. For example, linear support vector machines have a distinctly linear boundary with a broad and consistent gradient of class probabilities. Differently, the random forest yields nonlinear and somewhat blocky and sporadic-looking boundaries and class probabilities. In the second dataset, we can see how the algorithms try to tackle this distinctly nonlinear pattern of concentric circles. The first thing to notice is that our linear support vector machine, which assumes a linear model, is not doing well in this problem at all. However, other algorithms that have a more flexible model representation are better able to tackle this problem. In this particular case, nearest neighbors yielded the highest testing accuracy. Now, looking at the third dataset, we see another example of algorithms dealing with nonlinearity. Here, nearest neighbors, decision tree, random forest, and AdaBoost all achieved similarly high testing accuracies. However, linear support vector machine and naive Bayes are performing least well. Here we have a more detailed overview of many of the commonly used supervised machine learning algorithms designed for predictive modeling. Specific algorithms here are grouped roughly into families, and the arrows indicate some close relationships between some of the algorithm groupings. Feel free to pause the video on this slide to take a closer look at some of these algorithms. Again, focusing on the primary topic of this lecture, tree and rule representations are commonly used in machine learning, where inductive learning can be applied to train these representations to store probabilistic relationships from specific examples. Algorithms that use tree representations include examples like decision trees, random forests, and gradient boosting trees. Algorithms that use rule representations include examples such as Ripper, association rule learning, artificial immune systems, and learning classifier systems. Outside of machine learning, these representations can also store existing expert knowledge for use in reasoning systems, such as expert systems or other knowledge-based systems. This existing knowledge could either be certain for using deductive reasoning or uncertain for using inductive reasoning. Now let's focus on tree representations in particular. It's worth noting that we can think about and define decision trees in 2 ways. The first is as a decision support tool, which is simply a knowledge representation framework that presents information to facilitate decision-making. Consider this example where we want to decide what resource to use in making a home repair. At the top of the tree, we ask, does it move? If it doesn't, then we ask, should it? And if so, we want to use WD-40. And if not, there's no problem. Alternatively, if we answered yes to does it move and no to should it, then we'd want to use duct tape in this case. As a decision support tool, decision trees like this simply lay out the decision-making process based on existing knowledge. Differently, the term decision tree also refers to a supervised machine learning algorithm that learns from data and trains a model that can be used to make decisions and/or predictions. Here on the right, we have a decision tree trained on patients who tested positive for COVID-19, and we're trying to predict which patients will be survivors versus non-survivors. And in this model, 3 features were found to help make this classification: LDH, which stands for lactic dehydrogenase, NLR, or neutrophil to lymphocyte ratio, and CRP, which is a C-reactive protein. As a starting point, let's review the terminology used in decision tree algorithms. Here on the right, we can see the basic architecture of a simple decision tree comprised of nodes and branches connecting to nodes. The top of the tree is referred to as the root node. This is the starting point of the tree where all instances start during training or when applying the model to make predictions on new data points. Below this root node, instances will subsequently get divided into sets, ideally with a more homogeneous outcome. Next, we have the term decision node. This refers to a node, including the root node, that splits into further subnodes below it. Decision nodes are also referred to as sub, internal, split, or chance nodes. We also have the term leaf node, which refers to any node that doesn't split any further. These are also the points at which the outcome predictions are made on instances using the tree as a model. Leaf nodes are also referred to as terminal or outcome nodes. Let's also cover some other useful decision tree terms. First, we have splitting, which refers to the process of instances in a decision node being further split into subnodes directly below it. Then we have the terms branch and subtree, which simply refers to some subsection of the overall tree. For example, the subsection highlighted by this dotted line box. And lastly, we have the terms level and depth that refer to the level in the tree at or below the root node. And we can see these levels labeled here on the far right. This number also identifies the number of splits in the tree that occurs before coming to a prediction. Decision trees take a divide and conquer approach to the training or use of the tree in decision making. To progress down the tree towards a decision, a feature value is typically compared to a numerical constant or category value. For example, in this illustration, does x equal 1? However, there are other less common possibilities, including comparing the values of 2 different features or using a function of 1 or more features. Leaves represent the consequent, and these can output a conclusion, a class, an action, or some set of these. Leaves can assert either a certain conclusion or a probability distribution that specifies the support or certainty for a given consequent. Again, a certain conclusion would employ decision trees for deductive reasoning, while a probability distribution is a hallmark of inductive reasoning. Whenever we have a new instance that we want to make a prediction on using our tree, it comes in through the root node, and based on the values of that instance, we answer each test and find a path through the tree until we get to the right consequent, which represents the decision made by the decision tree. Notably, that new instance has to have the feature values that are specified in the tree. In other words, if the instance that comes in doesn't have a value of x, then we can't proceed. You can actually think of this process as being similar to instantiation from the field of logic. Staying on the theme of logic, you can also think of decision trees as a hierarchy of implications. For example, if x equals 1 and y equals 0, then A. Note that the caret symbol here represents a conjunction, meaning and. This implication describes a specific path through the tree to a conclusion A. On the right, we have all 4 of the implications that describe the 4 different paths through this decision tree. Effectively, from the perspective of logic, a decision tree can be viewed as a disjunction of conjunctions of constraints on the feature values of an instance. The of constraints on feature values alludes to the fact that we're assigning these features specific values, and the disjunction component of this definition alludes to the fact that there are multiple ways to end up as A or to end up as B. Let's take a quick step back and look at how decision trees can be split based on whether we're looking at a categorical or a numerical feature. First, it's worth noting that basic decision tree implementations only split into 2 other nodes. However, some implementations allow splitting into more than 2. In this example, we have a categorical feature, specifically sex assigned at birth. For the purpose of this illustration, let's imagine that we only have sex as male and female, and thus we have a split, or test, defined by a binary choice of whether sex is female, yes or no. For continuous valued features, such as age, we'll define this split with some kind of threshold or cutoff. For example, is age greater than 25? This again gives us the discrete choices of yes or no for proceeding further down the tree. For categorical or nominal features, the number of subnodes, for example here in this situation where we have weather connecting to sunny, cloudy, or rainy, could also equal the number of possible feature values. In this situation, a given categorical feature typically won't be examined more than once within the tree as a whole. However, it's worth noting that many decision tree algorithms only allow splitting into 2 possible subnodes. In such cases, any categorical feature with more than 2 possible values would need to be re-encoded as a set of binary features using something like one-hot encoding. This will ensure that the algorithm treats categorical features correctly. Another less common possibility, in some decision tree implementations, is that a categorical feature with multiple states could create a split that divides 2 subsets of states. For numeric or continuous valued features, as we saw, we test whether a value is greater or less than a constant, but as a result, that feature might get examined more than once. For example, here, petal length is less than or equal to 2.45 gives us our first split. But then the tree might later split petal length based on it being less than or equal to 4.85. Alternatively, similar to with categorical features, here a decision tree might less commonly be implemented to perform a single split based on a single feature into 3 or more value ranges. Now let's take a look at how decision trees make a prediction based on the leaf node arrived at. We start with a classification tree, where our target outcome is categorical or nominal. For example, is a patient sick versus healthy? Here we have an example of age being greater than 25, yes or no. Based on the training data or prior evidence supporting the conditions through a branch of the tree, each leaf node indicates the proportion of instances that ended up in that leaf, which translate to the class probability. Typically, the majority class found in a leaf is what gets predicted by that leaf. However, this can also depend on how the decision threshold of a tree is set. It's also worth noting that some decision tree implementations allow for multiple possible class outcomes. Alternatively, trees can be tasked with regression, or predicting a quantitative or numeric outcome, for example, patient height. Differently here, the tree looks at all the instances that ended up in a given leaf node and takes the average value of their outcome variable to be the leaf node prediction. Now that we have a sense of how decision trees work and how they represent knowledge, let's take a quick look at how a constructed decision tree would be used to make predictions on either training or testing data instances. In this visualization, we can see an existing tree structure. The blue and green dots entering from the top of the tree first represent training instances, and then second testing instances, upon which the tree is seeking to make class predictions of either class green or class blue. Instances are sorted down a single branch of the tree based on whether its value yielded a yes or no for each decision node condition, until a leaf node is reached. Leaf nodes in this tree are identified by a tiny vertical blue or green line, which does not branch any further. Based on the leaf node reached, instances are sorted into predictions of either one class or the other, and we can see the resulting training accuracy or testing accuracy at the bottom of this visualization. As mentioned, training data is first passed through the tree, with the training accuracy reported as 100%. And then next, testing instances are passed through the same tree, yielding a testing accuracy of 89.7%. This lecture is focused on how decision trees represent knowledge and how a decision tree can be used to make predictions. While there's a lot more to be learned with respect to how to train a tree as an inductive learning process, we will leave that to another lecture. For a more interactive explanation of how decision trees work, check out the link at the bottom of this slide, which will bring you to a visual introduction to machine learning focused on decision trees. Before moving on, let's take a quick look at how a decision tree, that was manually constructed with expert domain knowledge could be used in a real-world application. In particular, here is a tree that's been constructed in order to help solve a health economics question. Specifically, the research question in this example asks, which is the more cost-efficient treatment for hip replacement patients, heparin or conventional treatment? For some background, treatment with heparin is being considered for the prevention of deep vein thrombosis, or DVT, in hip replacement patients. Heparin can be injected pre-surgery and for 7 to 10 days post-surgery to try and prevent blood clots. However, there are risks of bleeding with the heparin treatment. So this tree takes in hip replacement patients, looks at whether the action was either heparin or conventional treatment, then further divides patients into whether they had deep vein thrombosis or not, and lastly whether they had bleeding or not. Now added to the tree are probabilities of these different situations, based on evidence collected by domain experts. This probability equation is given here in the bottom left-hand corner. For example, within the heparin branch, 86% of patients had no deep vein thrombosis, and of those, 90% had no bleeding. This kind of expert knowledge is usually derived from published studies, including existing data, such as clinical trial data or observational data, or it could come from meta-analysis, which is aggregated data from multiple sources. Note that the probability for all branches out of a given decision node add up to 1. Lastly, the leaf node down every branch represents the total cost for a patient having ended up with that specific set of conditions or events. Here, it's assumed that the cost of heparin treatment is $300, the cost of conventional treatment is $50, the cost of dealing with a deep vein thrombosis event is $2,000, and the cost of dealing with bleeding is $500. Consequently, this tree can be used to conduct a cost-benefit analysis, weighing the risks of patient complications to total expected costs. Further, it could be used to perform an analysis of costs with respect to quality of life improvements, in order to calculate, for example, the cost per expected quality adjusted life years, as examined further at the link at the bottom of this slide. One of the greatest strengths of a decision tree is that it's one of the very few algorithms that generates models that can be described as being truly interpretable. Truly interpretable models can typically be expressed as conditional rule expressions, known as implications from the field of logic. And indeed, decision trees can easily be linearized into decision rules. Each rule will capture a unique path from the root node to one of the leaf nodes in the tree. And the outcome of each respective rule will be the prediction found at the leaf node in the path through the tree that was followed. Here we have the format of a typical conditional rule expression, also known as an if-then expression, where the conditions are identified after the if, and these conditions are connected by ands, and then the predicted outcome follows the then part of the rule. On the right, we have another simple decision tree example, in this case deciding what to do based on the weather. Let's look at a couple of rules that can be linearized from this tree. Starting at the root node, we have, is it raining? If the answer is no, then we have our decision, don't bring anything. This is the shortest branch in our tree. Or instead, if it's raining yes, and is windy no, then we have the decision, use an umbrella. We could further make rules for every unique branch of this tree, where each rule conveys a clear explanation of the factors and their values leading to some specific decision. Now let's review the advantages of decision trees as a representation. First, they are easy to understand as an algorithm, which closely mirrors how human decision-making takes place. They're also a simpler, more compact representation strategy on whole. They're also highly interpretable and transparent as a model. They also can be useful in data exploration, in other words, as a quick strategy for getting familiar with the relationships in your data. They also handle different structured data types flexibly. They are a non-parametric representation, so they don't necessarily assume linearity. When used as a machine learning approach, they automatically internally conduct feature selection. Also, they train as machine learning algorithms quickly and efficiently, even on large datasets, and similarly, they make predictions quickly. As a manually constructed knowledge representation, they're relatively easy to create, understand, and interpret, and they can also be linearized and represented as if-then rules. They also offer an intuitive visualization strategy for knowledge and reasoning as a decision-making process. And decision trees can either be learned from machine learning or engineered based on prior domain knowledge. Disadvantages of decision trees can include the fact that they can be difficult to engineer rather than train, especially for more complex tasks. They can be difficult to update with new knowledge, and rather likely need to be rebuilt or retrained from scratch. Also, they're generally not suitable for representing large or complex knowledge bases. And when it comes to learning decision trees by induction, learned decision trees can of course contain errors. Also, this machine learning approach is prone to overfitting when trained, and many instances or examples are often needed to help reduce overfitting. Also, only one feature at a time is tested during the decision-making process, and this leads to the algorithm being considered myopic and not well suited to capturing complex associations in data, such as feature interactions or epistasis. Decision trees also tend to be biased towards features with more categories, in particular when using the Gini index for machine learning to train trees. And lastly, decision trees are not particularly robust, meaning that small changes in the training data can ultimately lead to large changes in the resulting trained tree and the predictions that it makes. In our last section of this lecture, we'll move on to rules as a form of knowledge representation. Rules are quite straightforward. They're typically given as if-then expressions. For example, if one or more conditions, then some conclusion. They can similarly be represented as condition-action expressions. For example, if one or more conditions, then do some action. The term condition is also known as a premise, an antecedent, or independent variables, while the term conclusion is also known as an action, result, consequent, goal, outcome, or dependent variable. Rules themselves are effectively propositional or first-order logic implications. Here's a really simple example of a rule. If the traffic light is red, and you've stopped, then a right-hand turn is okay. A quick biomedical example might be, if patient has high levels of the enzyme ferritin in their blood, and patient has the cis2a2 tyrosine mutation of the HFE gene, then conclude patient has hemochromatosis. The first two conditions given after the if statement are separate propositions, which if true, indicate that our consequent, or conclusion, is also true. Let's dig a little more into the rule's antecedent, or its condition. This is the if part of the rule. The antecedent represents a series of tests to be conducted, not unlike the tests at each decision node of a decision tree. As we've seen, there are natural links between rules and trees, and in the context of expert systems, rules are a popular alternative to decision trees as a form of knowledge representation. The antecedent tests are usually logically and together. This is similar to the definite clauses from logic used for chaining inference. However, in certain circumstances, rules can have different logical expressions within them, such as ors. Now let's take a closer look at the conclusion or the consequent of the rule. This is the then portion. And the consequent can either be a single conclusion or even a set of conclusions. Similarly, it can be a single action or set of actions. Additionally, where there is uncertainty, each consequent can have a probability distribution assigned by the rule, specifying the support or certainty for that given consequent. It's good to note up front that if you have multiple rules whose antecedents were satisfied, then you can end up with a situation where you have conflicts in terms of the separate consequence being asserted. This creates situations where we may need to deal with conflict resolution. Consequence can be used in a number of ways. One is to express a relationship. In other words, if the fuel tank is empty, then the car is dead. They could also be used to make recommendations. So for example, if the season is autumn, and the sky is cloudy, and the forecast is drizzle, then the advice is to take an umbrella. Consequence can also represent directives, or you can think of them again as actions. So in this case, if the car is dead, and the fuel tank is empty, then the action is to refuel the car. Further, consequence can be used to set up some higher-level strategy. As a rough example, imagine we have the scenario where we have if the car is dead, then the action is to check the fuel tank, at which point we can add the fact to the system that step 1 is complete. Then another rule in the knowledge base might say if step 1 is complete and the fuel tank is full, then the action is check the battery. And at this point, we add the fact step 2 is complete to the knowledge base. And lastly, consequence can be used as heuristics to represent some kind of prediction model, either for classification or for regression. As an example, we have if the spill is liquid, and the spill pH is less than 6, and the spill smell is vinegar, then the spill material is acetic acid. In this example, we have some evidence that is being used to support some prediction as to what the outcome material is, depending on the certainty of the facts, as well as the certainty of the association between the facts and the outcome. While we don't show these certainty values here, we'll explore rule uncertainty in another lecture. The consequent or prediction at the bottom here could have some certainty associated with it, going from 100% confidence down to something much lower. This table gives a summary of the basic information about the two main parts of a rule. It includes information about names of these two rule parts, for example, antecedent versus consequent of the rule, the nature of these two parts of the rule, where the conditions of an antecedent are similar to declarative knowledge, and the consequent are resolutions similar to procedural knowledge. Then, in terms of size of the parts, the antecedents have one or more if conditions, typically linked by ands, and the consequents usually have only one conclusion, but this is not always the case. And in terms of statement, we have the two most common kinds of connectors found in rules, and or, where in the case of ands, all conditions must be true for the conclusion to be true, but for ors, any of the conditions being true will lead to the conclusion being true. We can also add a variety of conditional relations to rules, such as equals, greater than, less than, or not equal. Rules can compare feature values to a constant, for example, temperature less than 45 degrees. These would be called propositional rules, which have the same expressive power as in propositional logic. For example, if credit rating is high, and salary is more than £30,000, or assets are more than £75,000, and pay history is not poor, then approve a loan up to £10,000 and list the loan in category B. This is an example of rules that have variables that get filled in and compared using conditional relations to a constant built into the rule in order to determine the truthfulness of this rule expression. But what happens when we want to solve a problem that involves relationships between multiple variable features? These can't be expressed with simple propositional rules, and a more expressive representation is required, similar to those we'll find in first-order logic. Fortunately, we can do this pretty simply in rules. For example, if width is greater than height, then the consequent is a person is lying down. Or if height is greater than width, then the consequent is that a person is standing up. This is a simple example of rules that might be trying to determine how a person is positioned. This kind of rule representation generalizes better to new data. But unfortunately, searching for relations between features can be computationally expensive. One simple solution could be to add extra features to the data via feature construction. For example, to add a feature which already checked whether width is greater than height, yielding a single variable that is a true-false value. However, you could also use variables and multiple relations similar to what we see in first-order logic. For example, if height and width of function xhw and h is greater than w, then the consequent is that a person x is standing. Here, the first condition expression indicates whether we have the height and width of person x, and the second condition asks if their height is greater than width, which is ultimately used to conclude whether person x is standing or not. It's also worth noting at this point that there are also some other less common rule forms that you might encounter. For example, sometimes rules can be presented with the conclusion first, given as conclusion if condition. So in other words, your chance of being audited is high if your income is high. You might also see rules that include the else expression. For example, if your income is high, or your deductions are unusual, then your chance of being audited is high, or else your chance of being audited is low. This has a similar structure to if-then-else loops that come from computer programming. You can also have situations where the action or consequent of a rule will actually trigger other rules or multiple actions. So for example, you could have a rule that triggers, then approve the loan, and refer to an agent. In this case, two actions are presented. Now let's start to think of rules as a collective group that form a knowledge base from which we can work from. First off, let's consider that there are two ways of executing a rule set. First, you can have an ordered set of rules. This is also known as a decision list. In this situation, the order of rules is important for how it's interpreted. Differently, we can have an unordered rule set. Here, rules can overlap and lead to different conclusions for the same instance. In other words, introduce conflicts. However, there are some benefits to having an unordered versus ordered rule set. Another thing you can do with a knowledge base of rules is to rely on default rules. This tends to be common when using ordered rule sets. Basically here, the idea is that you create rules for other outcomes, and if they're not satisfied, then a default rule with a default action or conclusion is triggered. Here's an example where a default rule is used. In this case, we have two rules, the second being a default rule that triggers whenever X is empty, or no other rules have been triggered, giving us a backup consequent, and potentially allowing us to implement a knowledge base with a fewer number of overall rules. Let's look a little further at this idea of default rules from the context of problems where we have a Boolean class or Boolean outcome. So the assumption here is that if an instance doesn't belong to class yes, then by default, it belongs to class no. What's nice in this situation is that we only have to implement rules that indicate when we have a situation where class is yes, and then just rely on the default rule for any situation where the class is no. In this example, our two classes of interest are class A and B, and so we only provided rules to indicate when we're part of class A, and otherwise the default rule of class B kicks on. In this situation, the order of the rules isn't important, and we don't happen to have any conflicts. Additionally, this set of rules is written as a disjunctive normal form. Specifically, we have two rules, both with antecedents using and, but either of these rules can be true in order for us to decide that we are of class A. Some uses of rules also allow exceptions. Let's take a look at an example using the iris dataset to get a better idea of how we might use exceptions. So here we have if petal length is greater than 2.45 and petal length is less than 4.45, then the class is iris versicolor. Let's assume at this point that all of the training instances we've looked at backs this situation up. However, maybe another instance comes along that isn't part of the class iris versicolor. Now, because the petal length here is 2.6, which would have fallen within the range specified by the above rule, we could now come up with an exception to the above rule to make it accurate in this new case. Here is the modified rule with the exception. We've added the phrase, except if petal width is less than 1.0, then the class is iris setosa. Here, the presumption is that none of the other instances that were correctly classified by the first rule meet the conditions of this exception, and this can help us deal with special cases. In the context of rule-based systems, in practice, exceptions can get pretty unruly. Here is a more complicated example where a number of exceptions are used. In this case, we're using the default rule kind of in reverse, where we start with the default of iris setosa, and then indicate exception conditions where we want to conclude a different class of iris, specifically iris versicolor and iris virginica. The advantage of building rule systems using exceptions is that the rules can be updated incrementally. In other words, it can be easy to incorporate new data or to incorporate new domain knowledge. In terms of interpretability, people often think in terms of exceptions. Further, each conclusion can be considered just in the context of the rules and exceptions that lead to it. This locality property can be important for us understanding and interpreting larger rule sets. What we'll call normal rule sets don't offer the same level of transparency in terms of interpreting the rule base. So while using exceptions and rules can be beneficial to interpretability, they can also lead to extreme overfitting when you're developing a rule set, and they might require constant updates as new instances are introduced in the future. So at the end of the day, this might not be the best approach in particularly noisy or complex problem spaces. Let's take a moment to look at the big picture of how a normal rule base might be set up and interpreted. Each rule in a knowledge base represents an autonomous chunk of expertise. Each individual rule is conceptually linked through OR expressions. When these rules are combined and fed into what's called an inference engine, the set of rules behaves synergistically, being utilized collectively to make decisions and choose new actions. The use of rules can be viewed as a simulation of the cognitive behavior of human experts. As such, they are the predominantly used technique to formulate knowledge in expert systems, in particular rule-based expert systems and production systems. And furthermore, they're often used in conjunction with frames in the construction of expert systems. We'll go into rule-based and other expert systems further in other lectures. When it comes to rule inference, there are two principal types of tasks that imply the use of one of two typical control regimes. The first is forward chaining. This is a data-driven approach where we start with facts and determine applicable rules, and then apply applicable rules to generate new facts. But there's also backwards chaining, which is goal-oriented. Here, we look for rules which decompose the goal, and then we try to solve secondary subsequent goals until we've proven our original goal. You might initially wonder whether one of these control regimes is better than the other, but the answer to that question really depends on the application and the circumstances. As such, both are useful approaches that we'll want to keep in mind. An important part of using rules to make inferences is the process of rule matching. Matching is all about determining the applicable knowledge of the given situation. In other words, based on the knowledge at hand, which rules are relevant to look at further. Rules become activated or triggered based on the type of inference or chaining being used. In forward chaining, we're trying to match rule antecedents to the fact base that we have in hand. While in backwards chaining, we're trying to match rule consequence to facts in the rule base to either prove that our consequent is true or find other rules with the consequence then could be fired to prove facts we need for proving our primary consequence truthfulness. This sounds complicated, but don't worry, we're going to be examining forward and backwards chaining in more depth in another lecture. However, it's worth noting that this process of matching can be the most computationally expensive step. Further, matching often yields more than one applicable rule that needs to be considered, and in those cases, it would be put on an agenda of rules to be looked at in sequence. When multiple rules are applicable, these rule instances are said to be in conflict, and we need to use conflict resolution to pick one to fire. Firing is a term used in forward chaining to describe the execution of consequence of an applicable rule instance. In other words, if the antecedents of a rule are satisfied, then the consequent is added as a new fact through firing. It's also during the matching process that variables and rules acquire values similar to instantiation from logic. So what are the advantages of rules as a representation on whole? Well, first, they're simple and easy to understand, and naturally correspond to the way people often think of knowledge. Furthermore, they're very expressive. Another advantage is that rules are straightforward to implement in computers, and they allow for the modularization of knowledge so that an engineer of the system can just focus on the validity of individual rules one at a time, more than having to worry about a giant conglomeration of if-then-else loops or some other more complex type of model representation. So ultimately, rule-based systems are also easier to write and often easier to debug compared to many other representations. Another nice thing is that there are some formal foundations with respect to inference. However, for some of the variations of rule-based systems, but not all of them, the more creative you get in putting together a rule base, the farther you can stray from a formal system that allows you to make reliable inferences. Now let's review some of the disadvantages of rules as a representation. For one, simple implementations of rules are often very inefficient. In other words, we can modularize our problem too much to make our lives easier in putting the system together, but when it comes to putting it into action, the same system might be computationally more expensive than it needs to be when going through the whole searching, matching, and inference process. Also, some types of knowledge are not easily expressed as rules. Further, a large set of rules can become difficult to understand as well as to maintain. Also, Rule-based systems can also be memory-intensive as well as computationally expensive. And at the end of the day, they can still be difficult to debug since we might have to consider the nuances of how rules work together to make inferences rather than just being able to focus on the validity of individual rules one at a time. Recall in our discussion of trees that individual branches through a decision tree can be linearized into decision rules. This conversion of knowledge from trees to rules is generally very easy. You can derive a single rule for each leaf in the tree, and the tree as a whole defines a unique set of rules, each representing a path through the tree from root to a unique leaf. Here, the antecedent is the junction of values checked at each node of the tree, and the consequence is the class or action assigned by the leaf node, arrived through a unique path through the tree. One nice thing about the rules that you get from a tree is that it won't matter what order they're executed in. However, the resulting rule set that you get from decomposing a tree could be unnecessarily complex. In order to avoid this, you could prune a tree or a rule set to remove redundant tests or trees. But what about going from rules to trees? This is actually much more difficult. A tree cannot easily express a disjunction between rules, despite the opposite being true. Further, a given rule base might not have the same sub or superset of features required to assemble a representative tree structure. So, for example, keep in mind that when going from trees to rules, all rules will have the root node specified as part of each rule's antecedent. So what do we do if this wasn't the case in a rule set that we wanted to turn into a tree? It's simply not going to be possible. Finally, to summarize this lecture, there are many types of knowledge representations available for artificial intelligence to utilize. A knowledge base is a specialized repository that stores information designed for knowledge representation. In other words, not just capturing data, but also the relationships, rules, and logic to reason in a specific domain. Trees, in other words, decision trees, offer an interpretable and simple way to arrange information for decision-making and can be built using existing expert knowledge or trained as a machine learning algorithm. Rules offer a flexible and interpretable strategy to arrange and reason with information for simple or very complex tasks, which again can be built using either expert knowledge or trained via machine learning. And lastly, individual branches of a decision tree can be easily converted into rules. However, the reverse is not always true. I'm Ryan Urbanowitz, and thanks for joining me for this lecture. Stay skeptical, curious, and creative.